This is your presenter Asloob Mudassar, and I am presenting slide number 71 of the course on laser physics. Question is, discuss the physics of radiative, that is spontaneous, and non-radiative decay in a bulk semiconductor material. The answer is, let us define R nu d nu as the number of spontaneous emission events per unit time and volume with emitted frequencies lying in the range nu and nu plus d nu, and rho j of nu naught d nu naught as the elemental transitions with the transition frequencies lying in the range nu naught and nu naught plus d nu naught. We have defined rho j in the previous slide, and here it is the joint density of transitions. So rho j represents joint density of transitions, and we have defined this term in the previous slide. dr nu, which is an elemental contribution to R nu, is expressed in terms of rho j of nu naught d nu naught in the following form. So dr nu is equal to A21 multiplied by j of nu minus nu naught multiplied by fc of E20 prime multiplied by 1 minus fv of E prime 10 multiplied by rho j of nu naught and d nu naught. So let's explain the terms in equation number 1. A21 is the rate of spontaneous emission between the two levels, that is E20 prime and E10 prime, located in the conduction band and the valence band respectively, with the transition frequency nu naught. So you see that here we have written the subscript as 20 with E prime. This is the band lying in the, this is the level lying in the conduction band. So actually this is not a single level, but you may consider it as many levels, closely spaced and equally spaced. For example, 2-0 level, 2-1 level, 2-2 level, 2-3 level, 2-4 level, and so on. It depends upon the broadening, and here we are considering a homogeneous broadening, which means that we have these levels which are closely spaced. So E prime 20 is actually not a single level but many levels, as I said, and you see that these could be labeled as E20, 21, 22, 23 and so on. But you know that we are just talking the basic level of that level, which is, or the fundamental or the lowest level among those levels, and we have labeled it as E20 prime. And similarly E10 prime is a level in the valence band. So this is again is not a simple level, a single level, but it consists of many levels. For example, 10, 11, 12, 13, 14 and so on. And again, as said earlier, that these levels are uniformly spaced due to homogeneous broadening. So E20 prime and E10 prime are many levels, respectively lying in the conduction band and the valence band, and all these can emit a transition frequency of nu naught with the transitions. For example, the transition of level E prime 20 to E prime 10 will give you nu naught, and similarly the transition from E21 prime to E11 prime will give you the same frequency, and similarly the transition from E22 to E22 prime to E12 prime will give you the same transition frequency nu naught. So these are many levels, and these can generate and the combination of such levels can generate a transition frequency with the frequency nu naught. And g of nu minus nu naught is the line shape function of the transition. Due to the homogeneous broadening, this gives you the line width or the line shape function of the transition occurring at frequency nu naught. Spontaneous emission occurs between an occupied upper state and an empty lower state, and this is represented by the factor. So let me explain this factor. Rho Fc. You see that we have discussed this function f, which give you the probability and probability of occupation of a level, and we have discussed this function in the previous slide. So here we are going to explain that Fc of E20 prime is the probability of a level E prime 20 lying in the conduction band to be completely occupied, and 1 minus Fv of E10 prime gives you the probability that the level E10 prime in the valence band is empty, because we have 1 minus Fv. So we have, because we for the spontaneous emission we want that the level E20 prime should be occupied, and the level in the valence band, which is E10 prime, should be empty. So that's why we have written down their probabilities like this, that is Fc of E20 prime multiplied by 1 minus Fv of 10 prime. And then of course rho j of nu naught gives you the transition, transitions at the frequency nu naught, joint transition. So rho j gives you the joint transition at the frequency nu naught. So this is what we have described this term. So you see that all the terms in this equation 1, that is in the equation number 71.1, are explained. And you know that here we have given this on the left hand side as dr nu, which is actually the elemental transition, with the transition frequencies lying between nu naught and d nu. This is the elemental transitions, dr nu. And you know that here we have defined this term r nu d nu as the number of spontaneous emissions events per unit time, per unit volume, and volume, with emitted frequencies lying in the range nu and nu plus d nu. Now the total spectral rate r nu. You see that we have an expression for dr nu. Now we are talking about the total spectral rate r nu. We have called it a spectral rate because it is defined at a frequency nu. So the total spectral rate r nu is obtained by integrating the elemental contributions dr nu over all transition frequencies nu naught as given. So we have r nu calculated on the left hand, written on the left hand side, and on the right hand side we have the integral over here. That is, we are integrating both sides of equation number 1, and we have the integral on the right hand side, and all the terms are the same as in equation number 1, that is on the right hand side of equation number 1. And you know that we are integrating it with respect to d nu naught, because we are now going to sum up the contributions from all the transitions which are giving nu naught as the transition frequency, because we have explained that E prime 20 are many levels in the conduction band and E prime 10 are many levels in the valence band. And the transition from these levels in the conduction band to the levels in the valence band can emit transition frequencies nu naught. So we are summing up the contributions of all those nu naught frequencies emitted as the transition frequencies in equation number 2. Now in order to solve this integral, let's assume that g of nu minus nu naught is a much narrower function in comparison with the other functions in the integrand. That is rho j of nu naught, that is g of nu minus nu naught is narrower than rho j of nu naught, and also in comparison because there is only one function that we are comparing with. So g of nu minus nu naught is narrower than the function of rho j of nu naught. Then g of nu minus nu naught can be approximated to be delta of nu minus nu naught. So you see that when we are setting g of nu minus nu naught to be equal to delta of nu minus nu naught, it means that we are converting all these levels, that is the levels E20 prime to the single level, and similarly all the levels in the valence band represented by 10 prime will be converted to the single level, because we are, by setting g of nu minus nu naught to the delta function, we are assuming that the contribution of the homogeneous broadening is very small, that the function g of nu minus nu naught can be approximated by a delta function. So in order to solve, if you substitute g of nu minus nu naught in equation number 2 by the delta function, to solve this integral you set nu naught equal to nu, so that the integral can be solved. And since you are specifying the value of nu naught, a particular value, that is nu naught is equal to nu as the argument of the delta function, then you see that all the frequencies, all the functions with the frequency nu naught will be converted to nu, and the integral is solved because we have fixed the value of nu naught and the integral is omitted. So we have written this in equation number 3. So our nu on the left hand side is equal to A21 multiplied by Fc of E2 prime multiplied by 1 minus Fv of E1 prime, and then multiplied by rho j of nu. So here you will notice that there are many levels in the conduction band now has been represented by a single level E2 prime in the conduction band, and many levels in the valence band have now been written as a single level in the valence band represented by E1 prime. The spontaneous emission rate A21 is now defined at nu is equal to nu naught, and the energy levels corresponding to the transition frequency nu are E2 prime and E1 prime. The emission spectrum, that is the plot of R nu versus H nu minus Eg divided by Kt, is found wider than the gain spectrum, that is the plot of G versus H nu minus Eg divided by Kt. Here we are not giving the plots, but we are just mentioning that the emission spectrum is found wider than the gain spectrum. The gain, we have already calculated the gain in the previous slide. So here we are not mentioning the gain, but we are just specifying that the emission spectrum is now found wider than the gain spectrum. This is because G is proportional to Fc of E2 prime minus Fv of E1 prime. So in the previous slide we have noticed that the gain expression is in the gain expression G was proportional to this expression, that is Fc of E2 prime minus Fv of E1 prime, whereas R nu is proportional to, as can be seen equation number 71.3, that R nu is proportional to Fc of E2 prime multiplied by 1 minus Fv of E1 prime. So there is a difference between the two proportionalities, that is G is proportional to the first expression and R nu is proportional to this second expression. So due to that one, when we plot these functions, we found that R nu is that is the emission spectrum is broader than the spectrum given by the gain, that is the gain spectrum. So the emission spectrum is broader than the gain spectrum due to the difference of the terms as I explained. The total rate R, you see that here we calculated the rate which was labeled as the total spectral rate R nu, and we have summed up all the contributions giving the transition frequency nu naught, and we have written this R nu as a function of a frequency nu in equation number 3. And now we are going to calculate the total rate R is obtained by integrating R nu over all emission frequencies. So here we are summing up all the emission frequencies, and this now capital R without the subscript nu is equal to the integral of A21 multiplied by Fc of E2 prime multiplied by 1 minus Fv of E1 prime and multiplied by rho j of nu and d nu. That is, we are integrating both sides of equation number 3 with respect to frequency nu. So this R nu will then be represented by capital R, because this is the total rate R. Functional form of capital R from equation number 71.5 cannot be computed in the present case. However, phenomenological relationship is given in equation number 5. That is, R can be written as capital B multiplied by NE multiplied by NH. And here we are assuming that the contribution of the holes, that is the concentration of the holes, is the same as the concentration of the electron density. So we are setting NH equal to NE, and that's why we have R equivalent to B multiplied by NE square, where B is some constant. This equation holds well at electron and hole densities of interest. However, in the recombination process of electrons and holes, the K selection rule does not remain valid. And by definition, the rate is given by the rate equation can be written as, so dNE over dt, that is the rate of decay of the density of electrons in the upper states in the semiconductor material, is equal to minus R, where capital R is given by equation number 5. And now we are substituting the value of R over here, which is equal to, so we have a minus R, we have a minus B into NE square, and this can be written as in terms of the lifetime as minus NE over tau R. Because we have NE square, so we have used 1 NE over here in the equation on the right hand side, and the rest of the term has been absorbed in the lifetime expression tau R, where tau R is the radiative lifetime and is found to be tau R is equal to inverse of B into NE. So this is what we have given the rate equation in case of the spontaneous emission. Non-radiative transitions occur at deep impurity centers, not located on the surface of the semiconductor, but well within the semiconductor. So that's why we have called them, that is, we are considering non-radiative transitions to occur at deep impurity centers, where an electron or a hole is trapped, resulting in deep trap recombination. At sufficiently high doping, where the Fermi level approaches the conduction band, the trapped electrons in the conduction band recombine with holes, resulting in non-radiative transition. Excess energy is transferred to the lattice. Direct recombination of electron hole occurs in small gap semiconductors, where excess energy is transferred to another electron or hole, raising them to higher energy states in the relevant bands. This recombination is referred to as the Auger recombination. The decay rate of electron density is given by, for the case of non-radiative decay, the decay rate of electron density is given by dNE over dt is equal to minus capital C multiplied by NE multiplied by NH multiplied by NE. And again we are assuming that the density of holes is the same as the density of electron, and we setting these one, we have dNE over dt is equal to minus C times NE cube. And this NE cube can be written as 1 NE can be separated out, and the NE square can be written in the form of, can be absorbed in the expression of the lifetime, the Auger recombination lifetime. So this can be written on the right hand side as equal to minus NE over tau A, as given in equation number 7, where C is some constant. Non-radiative lifetime due to Auger recombination represented by tau A is given by tau A is equal to inverse of CNE square. So you see that here we have calculated the two decay rates, one due to spontaneous emission given by equation number 6 and the other due to non-radiative decay rate given by equation number 7. So this completes the solution of the question. So this is the end of slide number 71.